Welcome to our first lecture of the Electrical Engineering Workshop. Today we will cover the basics of electricity and then go over a few electrical components and explore how they work in a light bulb demonstration. So our world is built of atoms. Atoms are very small and contain protons and electrons. Protons have a positive charge and electrons have a negative charge. Like magnets, protons attract electrons and repel other protons. The same thing goes for electrons. They attract protons and repel electrons. A wire is made up of metal atoms. We can think of the protons in these metal atoms as fixed charges, and the electrons as moving charges. We define current as the flow of charge, but since electrons are negatively charged, their direction of movement is actually the opposite of the direction of current. We can measure this flow of charge, which has units of amperes, and we abbreviate amperes as the letter A. Although voltage is more complicated, for now we can think of it as a pressure pushing electrons through a circuit. In our last slide, we talked about how current is just the opposite of the flow of electrons. Since voltage pressures electrons into flowing, we can also think of it as the driving force behind current. A battery creates a voltage. When we put a battery into a circuit, it creates a current that flows out of the positive end of the battery. An example battery is shown here. The longer side represents the positive end of the battery. So in this case, current would be going up and out of the battery diagram. Going back to our definition of current, which way do you think the electrons flow? Go ahead and pause the video and see if you can figure out whether electrons flow out the top or the bottom of the battery as shown. Because current flows in the opposite direction to the flow of electrons, we know that electrons flow down from the bottom or the negative end of the battery. Unlike voltage, resistance does not drive current, instead slows it down. Resistors resist the flow of electrons. Think about trying to move in water, where water is the resistance. It's a lot harder than moving on land, right? We can also measure resistance, and that weird symbol that looks like an O is called an ohm. And the squiggly line at the bottom is how we draw a resistor on a circuit diagram. Circuits are complicated, but this analogy might help you understand how they work. We can think of water as an electric charge, and the flow of water as electric current. Batteries make differences in pressure that can push water, creating a current. Current is how much water, the volume of water, that flows through a slice of the pipe over time. Resistors reduce that flow of water. If we put all the concepts of resistance, voltage, and current together, we can start to understand the basic principle behind a circuit. Even if you've never built a circuit before, if you've heard of one before, you'll most likely think about wires. Wires are very conductive and have close to no resistance. Here is a basic circuit that has a battery, which has V next to it and that stands for voltage, and it has a resistor, which has an R. As you can see, the wire goes all the way around and connects back to the battery. If the wire did not connect back to the battery, there would be no current, because charge cannot flow off the wire. The resistor reduces the current in the circuit. We can calculate the current through the wire through Ohm's law, which states that voltage equals current times resistance. If we divide resistance from both sides of the equation, we find that current equals voltage divided by resistance, or more simply, I equals V over R. Let's say we knew the current and the resistance, but we didn't know the voltage of the battery. We could use Ohm's law to figure out the voltage across the resistor, which would be I times R, and this is the same as the voltage in the battery. If we have multiple resistors or other components in a circuit, we cannot just use Ohm's law for one resistor to find the current and the voltage of the whole circuit, as we did on the previous slide. We now will have to use Kirchhoff's voltage law to find an unknown quantity. Let's say we are looking for the current in a circuit with two resistors of known resistances. We have to let the current be a variable called I, and then find the voltage drops using this variable and the known resistance for each resistor. Then we take the voltage of the battery and subtract off both these voltage drops to make the equation equal 0. So in our last slide, we went over a term, voltage drop. But what actually is a voltage drop? Basically, when you pass a current through a resistor, it has a negative voltage, hence a voltage drop. In order to calculate a voltage drop, we use the equation V equals I times R. This might look kind of familiar from slide 9, but you will see that everything actually makes sense. Using Kirchhoff's voltage law, we see that V minus the voltage drop of the resistor equals 0. Thus, V actually equals to the voltage drop of the resistor, which also equals to IR in this case. So this problem is really similar to the concept we just went over. We have 5 volts total and a resistor of 3 ohms. 5 volts minus the voltage drop of the resistor equals 0. Therefore, the voltage drop of the resistor equals to 5 volts, and we have I times R equals 5. If we do some quick division, we see that the current is 5/3 amps. So now we're getting into some more complicated examples where we have more than one resistor, but really this is no big deal. Just always remember that resistors have voltage drops, which mean negative voltage. So we have 5 minus the voltage drop of resistor 1 minus the voltage drop of resistor 2, and that all equals to 0. Because current is the same everywhere in this loop, we can let current be a variable called I. Then the voltage drop of resistor 1 is the current, which we just called I, times its resistance, which is 1 ohm. Similarly, the voltage drop of resistor 2 is I times 2 ohms. That means that we can subtract 1I and 2I from 5 and set this equal to 0. After some algebra, we find that the current is 5/3 amperes. For this workshop, all problems work out such that you don't have to worry about units, and you can ignore the V and the omega and the A when you do your math. Now it is your turn to do some practice problems. We will email you these, so just pause the video and continue once you've completed them. Another thing to note is that we never want to create a path in our circuit where there is 0 resistance. For example, in this circuit, if we follow the middle path of the wire, we can see that there is no resistance from the positive to the negative side of the battery. This is really bad and can lead us to break our batteries. So always be careful when you are building your circuits to avoid this. Now we will introduce breadboards. Breadboards are tools that already have electrically connected holes. So when you plug components into these holes, they can be part of a circuit. The general rules of a breadboard are that the plus and minus columns are connected vertically, while every row with A, B, C, D, E, and the same number are electrically connected. The same goes for F, G, H, I, J, but rows in A, B, C, D, E are not connected with the rows in F, G, H, I, J. A switch is another component, but it functions very differently from a resistor. Remember how a wire has to go from one end of a battery all the way to the other in order for current to flow? A switch can turn on and off current in a circuit. For our labs, we will use buttons, which are very similar to switches. This is what a button looks like on a breadboard. As you can see, on the image to the left, the button connects the first and third rows when it is pressed down. When it is not pressed down, the rows remain unconnected. For general safety with breadboards, always make sure to have no short circuits by adding resistors. Circuit components can heat up, so we'll always check your circuit first before we connect the battery to your breadboard.
Now we will go over our light bulb lab. A light bulb is another component that acts like a resistor but produces light too. In this first part of the lab, we will make the light bulb light up using rows 1 and 5 of the breadboard. So inside of your kit bags, find 2 jumper wires, a light bulb, and a breadboard. The light bulb is really small, so be sure to not lose it. I know our slides contain batteries, but we will plug the batteries in when we verify your circuit. Again, just pretend like the battery is connected in this configuration. We will put it in the exact place when we check your circuit. And just as some breadboard review, in the red column we can see that in this box everything is electrically connected, And in the blue column, in the black box, everything is electrically connected too. So now we want to plug our first wire into the red column and into the first row. Note that the entire row is electrically connected. So if I put anything in the same row, it will also be connected. Again, as some review, the red column hasn't changed, but now it's also connected to the first row, so A, B, C, D, E. And again, the black column is connected too. We will put our light bulb between the first and fifth row. You can use any hole as long as it's on row 1 and row 5. Again, that's because rows are electrically connected. If you pay attention to the red, everything in red is electrically connected, and that makes sense because the entire column is electrically connected, and we connect the column to the first row with the wire, and then the light bulb connects the first row to the fifth row. And again, the entire black column is electrically connected to itself, but not to the red yet. Use another jumper wire and connect row 5 to the negative side of the battery. As we verify your circuits, each light bulb should light up. And finally, everything in blue is connected. Next, we want to incorporate a button into our circuit. When we press the button, we want to turn on the light bulb. From your previous circuit, remove the last wire connecting the light bulb to the negative side of your battery. Now add a button that will connect row 5 and 7 if it is pressed. Finally, connect the other side of the button on row 7 into the negative side of the battery. When you push the button, the light bulb will light up. Notice how when the button is not pressed, the light bulb does not light up because rows 5 and 7 aren't actually connected. Next, we want to see if we can add another button. We want our light bulb to turn on only if we press both buttons. If we press only one button, the light bulb should not turn on. Again, remove the last wire that connects back to the negative side of the battery. Add another button in sequence with the previous button. This should go from row 7 to row 9. Now attach a jumper wire to connect row 9 to the negative side of the battery. Notice how both buttons need to be pressed in order for the light bulb to light up. Instead of pressing both buttons to turn on a light bulb, we want to make a circuit where we only have to press one button. First, start by connecting the positive side of the battery to a row. It can be any row, but try to position it on an A position to make space for the next steps. Now, add a button from that row to another row. In this case, we are on row 5 and 7, but it is really up to you. Now add the light bulb. And connect that end back to the negative side of the battery. Now this should work, but we only turn on the light bulb when we press one button because we only have a button in our circuit. So let's add another button. Do you know where this button should go? So this might seem a little confusing, but if we think about it, putting two buttons side by side like this makes sense. If either one is pressed, we will establish an electrical connection between rows 5 and 7, turning on the light bulb. And that's it. Thank you for watching.